Okay, so now after discussing exactly how angles come to be and exactly how we orientate them strategically in space by using the Cartesian plane so that we can simplify all of our calculations, now I want to move on to trigonometric ratios. Now, when trigonometric ratios were defined, they were defined using the Cartesian plane. Hear me out. We'll first use the Cartesian plane to define these trigonometric ratios, and then we will use the trigonometric ratios and define it for any right angle triangle. Understood? So exactly as I said, that you can take any angle in space, orientate it strategically using a Cartesian plane, and you'll be able to define it accurately. So exactly as I said, that you can take any angle in space, orientate it strategically on a Cartesian plane, and we'll be able to simplify a lot of our calculations. It's the exact same idea. So we're going to start defining it from the Cartesian plane. Once we have it defined for the Cartesian plane, then we are going to define it for any random triangle. Understood? So that's the beauty of maths, is that once we find a pattern, we can generalize and be able to find these trigonometric ratios for any right angle triangle. So it does not specifically have to be within the Cartesian plane. It can be orientated anywhere in space. Remember, it's the same right angle triangle, but just in a different position. Understood? Let's look at sine, cos, and tan. When you look at the Cartesian plane, sine of theta, see, sine of theta is defined as y over r. Now be very careful with the word I'm using. I said it is defined. Do not change the definition. That's the definition of it. Exactly like how we have definitions of words in the dictionary, this is a definition of sine. And the reason we say trigonometric ratios is because the sine of some angle, whatever the angle may be, is equivalent to the ratio of the opposite side, the y, and the hypotenuse, the r. The cos of some angle is equivalent to the adjacent side, x, over the hypotenuse, r. Understood? So this is why we call them trigonometric ratios, because this trig function is equivalent to some ratio. What ratio? The ratio of the x over the r, right? And then tan, the trigonometric ratio tan, is defined as y over x. So therefore, the tan of some angle is equivalent to the ratio of the opposite side and the adjacent side. Now, this is what I meant by, when I told all of my sections, I said that the sine of theta is what? Is the same as y over r. So that means wherever I see y over r, I can put in sine theta. Now, because you see this notation, you may get confused and think, okay, what is sine of theta? Sine of theta is this. That's what it is. So when I put sine of some angle, it must give you some ratio. Understood? What is cos of theta? Cos of theta is very confusing. It's a new notation to me. It's just a new notation representing what? This ratio. Tan of theta. Tan of theta is confusing to me because it's a new notation. But what is tan of theta equivalent to? It's equivalent to y over x. Understood? Right, then what we get what we call reciprocals. The reciprocal of 1 over sine is cosec. So basically, if I say 1 over sine, will give you cosec of theta. So cosec of theta is equal to 1 over sine of theta, which is equal to 1 over y over r, which is equal to r over y. Right? The reciprocal of cos is sec. Sec of theta is equal to 1 over cos theta, which is equal to 1 over x over r, which is equal to r over x. Then we have cot. Cot of theta is equal to 1 over tan of theta. 1 over tan of theta, which is equal to 1 over y over x, which is equal to x over y. How did I go from here to here? Very simple. I'm saying 1 divided by y over x. What do? We multiply by the reciprocal of the second fraction, which is equivalent to x over y. Understood? I've talked about this property under the fractions, grade 9 fractions video. So it should not be foreign to you now. Yeah, so that's what we have. So we have the ratio, we have the reciprocal of the ratio, we have the ratio, have the reciprocal of the ratio and the reciprocal. Right? Now, that's looking at a triangle within the Cartesian plane. So using x and y coordinates. If we are defining the triangle more generally, right? More generally, there's theta here, there's y, there's x, and there's r. Okay, now let's define these trigonometric ratios for any right angle triangle. There's something that's very important. You have to look in terms of the angle that you're given. See this angle here, in terms of this angle, that is what we call the opposite side. This is what we call the adjacent side, and this will always be the hypotenuse. The hypotenuse is the side opposite the right angle, right? So what we can say is that if you're given this angle theta, in accordance to this angle, sine is equal to what? Opposite over hypotenuse. So sine of theta is equal to what? Opposite over hypotenuse. What is cos of theta equal to? Adjacent over hypotenuse. And tan of theta is equal to opposite over adjacent. Understood? Now, what I could have done was now, I can say, okay, what if I gave you alpha here? If I gave you alpha here, then sine of alpha will equal to what? This becomes the opposite side. Understood? That becomes the opposite side. This becomes the adjacent side. So it's always in relation to the angle that is given. From the eyes of this angle, what's the opposite side? That's the opposite side. This is the adjacent side. From the eyes of this angle, that's the opposite side, and this is the adjacent side. So it changes according to what angle we are talking about. X is the side between the angle and the right angle. So X is the side between the right angle and the angle. Right, so that's the X, or the adjacent side. Y is the side away from the angle. So what's away? That's the one that's away from it. It's the opposite the angle in question. And the hypotenuse is obviously the side opposite the right angle always. And this holds irrespective of the orientation of the right angle triangle. So I could have taken this exact right angle triangle. I could have orientated it like this. Right, so I took this point here and I flipped the entire triangle around this way. So this became theta. This becomes the right angle. Let's say I call this side here 1, 2, and 4. So where is 2? 2 is opposite the theta, so that becomes 2. Where is 1? 1 is adjacent to theta, so it'll be 1 there, and 4 will remain. So irrespective of the orientation, these numbers will still hold. This is why I said that all we're doing when we're using the Cartesian plane is we're orientating this random object in space on the Cartesian plane. We're putting it with precise coordinates. That is why from using these words opposite, hypotenuse, and adjacent, we use x, y, and r. Because we are defining it using these coordinates. Right? And a very useful mnemonic to remember is SOHCAHTOA. Sine is equal to opposite over hypotenuse. Cos is equal to adjacent over hypotenuse. Tan is equal to opposite over adjacent. Understood? Very, very simple stuff. So again, let's go over what I said. I said when we defined these trigonometric ratios, we defined it from the Cartesian plane. Sine is a trigonometric ratio, means it's equivalent to some ratio. What the ratio is? The ratio is y over r. Cos of theta is equivalent to some ratio. What's the ratio? X over r. Tan of theta is equal to some ratio. What that ratio is? Y over x. So wherever you see sine of theta, you can put in y over r. Wherever you see cos of theta, you can put in x over r.